momentum equations, we then want to have scalar equations also. And for the scalar equations, we can just do basically the exact same thing. We start out here, let's say, with a mixture fraction equation. We can derive a mean mixture fraction equation. And then we have two unclosed terms. Here, one is a molecular term. We typically neglect this. And then we have here what we call the scalar flux term. That's the same, that's the turbulent transport. That's the same as the Reynolds stress term in the momentum equation. And then, okay, guys, when you come in, you have to be quiet and quietly sit down. Okay, and then we have this turbulent flux term that needs to be modeled. And then, so we do the same thing we did earlier. We take the turbulent flux term and we use a gradient transport model. We express this as the gradient of the mean gradient of the quantity we want to transport times a transport coefficient here, and what we call then the eddy diffusivity, which is the same thing as the eddy viscosity for the momentum. And so how do we express this? Sometimes we just set it proportional to the eddy viscosity, because it's the same eddies that cause the mixing in the momentum and in the scalars. And there's a proportionality here of proportionality constant, the Schmidt number, turbulent Schmidt number, which is also order 1, and could be a fit parameter for tuning a model that it matches the experiment. And so then we get an equation like this, and you see this is now closed, everything known. Then we are interested in the distribution in the PDF, and we'll talk later about PDFs. We are interested in the distribution of mixture fraction. And for that, now we only know the mean. We also want to know what the variance is. And so we derive an equation for the variance that's shown here. You just take the local instantaneous equation. You subtract the mean equation that gives you an equation here for the fluctuation. You multiply this with the fluctuation and average it, and that gives you an equation then for the here for the variance. It's relatively easy to derive this. This variance equation now is basically, that's for the scalar the same as the kinetic energy was for the momentum, right? And so it has also similar terms. You have the turbulent transport term here. For this, we just use a gradient transport model. And then here, this we have already. That was the subgrid scalar flux. We had a model for this already in the mean equation. That's the production term. And then also we have a dissipation term. And that dissipation term, that is the scalar dissipation rate that we already introduced yesterday, where we talked about the flamelet model. And you see now what the physical relevance is of the scalar dissipation rate. It appears as the dissipation in the variance model. What is dissipation of variance? It basically means, let's say, if I have a variance in the mixture fraction, that means I have a region maybe where I have a little higher mixture fraction, and sometimes I have a little lower mixture fraction, okay? That's variance. And if that variance goes away, it basically means at the end everything is well mixed. I have no no regions of higher and no of lower, which means I've mixed these out. So the dissipation of variance means molecular mixing. That's what it is, okay? And that's why the reaction rate, we saw this yesterday, is related to the dissipation rate because it's the molecular mixing rate. And how do we express this? We need a model for this also. We can first define a time scale here. If we don't want to define a time scale, we can do this by using here the variance and the dissipation rate. In fact, the dissipation rate is a time scale already. This here is non-dimensional anyways, but if we finite time scale here for the turbulence, and we say we have a K epsilon model, then we only have K and epsilon. If I want to define the time scale from this, it is K divided by epsilon. So that's kind of the variance of the momentum fluctuations divided by the dissipation. And so here we define this in the same way. And then we say these two time scales, they should be the same. And then you see that this is the expression we get, okay? So, or they should be proportional. The time scale should be proportional, meaning there's a coefficient here. And that coefficient, you know, people use whenever they need the dissipation rate, they use whatever value fits the data, okay? So that time scale ratio C chi, that is used a lot to tune models, you know, to give you the right the results that you want to get. Okay, and so if we look at reactive scalars, same thing. We have the temperature equation, which shown here is the same as mixture fraction equation, except we have a chemical source term, which is given here by like this. And then we have so temperature equation. We also have mass fraction equations, which looks very much the same, especially if we assume unity Lewis number, and it also has a chemical source term. And then what we do here is we write this as just a scalar equation, and that, so we have a vector of scalars, and the vector of scalars has all the mass fractions we're interested in, plus the temperature. And then we have a vector here also of source terms, which is then the, you know, the source terms here for the mass fractions and for the temperature. But it means, you know, for all the scalars, we can just use this one equation. And so here we can do the same. We introduce the Reynolds decomposition, and we introduce it here in the local instantaneous equation, and then we derive the equation for the mean. And just like for the mixture fraction, you get the same terms. We have a molecular transport term that we usually neglect, and then we have a turbulent transport term. Here we use the gradient transport assumption, and then here we have the chemical source term, and that we keep for later. That we keep here for the chapter modeling of turbulent combustion. Okay, yeah, here gradient transport assumption and so on. So this gives us all these equations. Now for large eddy simulation, I have a section here on large eddy simulation, and we're a little bit behind, so I'll try to go through this quickly and maybe just give you the general idea of what large eddy simulation are. So direct numerical simulation, I mentioned this already. We solved the Navier-Stokes equations without any models. You know, Navier-Stokes equation augmented by the scalar equations we need. Everything is closed in these equations, and we need no models. And the problem is that we saw this earlier for large Reynolds number, the range of scales becomes very large. So a computational domain needs to be at least as large as the integral scale, and the mesh spacing needs to be as small as the Kolmogorov scale. And so the number of grid points in one direction is then roughly, let's say, given by the integral scale divided by the Kolmogorov scale. And we said that's Reynolds number to the 3/4 power. And this is in one direction. So in 3 dimensions, it's then this number cubed. And so the cost of a simulation, you know, of a turbulent flow goes with the Reynolds number to the 9/4. And then that doesn't even consider that you know, if you have smaller scales, you'll need a smaller time step also, which would add a factor 2 here in this again. And so so that's why you can do this only for small numbers. So for example, take a turbulent jet, Reynolds number 15,000, and so that means, so this is the jet Reynolds number that's formed with a bulk velocity and the nozzle diameter. And turns out the turbulence in a jet like this, the turbulence Reynolds number is roughly the jet Reynolds number divided by 50. And so, you you know, if I then determine here the number of mesh points I need is about 400,000, roughly 500,000, let's say, but that's only for one integral length scale, we said. So that would be for, you know, one little area like this. So if you want to compute the full jet, you need an awful lot of points. And 15,000, that's something we can do today, but and we have done, but you cannot go much larger, right? So that's roughly the limit of what you can do today, at least for reactive flow. So in large eddy simulation, we try to, so in Reynolds averaging we saw earlier, we just do a time average or an ensemble average, and all the fluctuations, the turbulent dynamics, are gone from the solution. And we put them back in through the back door through a model for the Reynolds stress tensor. In LES, we try to resolve part of the motions. And this gives an example here, wondering if that's playing, yeah? This is, you know, just a visualization of a simulation of a jet flame that we did some time ago. And so here you see the result from the simulation, and you see a certain averaging window, and the time, the averaging filter gets smaller and smaller, and now it's a little difficult to see, but this is roughly how this looks like. This movie is too long anyways, but what you see here is that this, in this large eddy simulation we did for this, it looks like all the turbulence is still there, but it turns out it's only the large-scale turbulence that's still there. The small-scale turbulence we don't resolve. And maybe I just show you this a little later. You know, a little more structure. So what we did here is actually we compute the radicals locally, and then we assume like you have chemiluminescence. So we assign to the different radicals the colors that they would usually radiate in, and then we do ray tracing to collect the light. There was a place here where, here. This is where you see a little bit the three-dimensional structure of this. And you know, one thing we did also, we did this from two angles then, in green, in blue and red. And then you can use these 3D glasses, you know, the red and blue glasses. And you can actually see this in 3D. I used to bring these to the, you know, to these kind of lectures, but at some point I gave up. It wasn't the same really as, you know, the metaverse or whatever, you know. So, okay, so this is what we do. So this here shows the red signal. Shows, I mean, it's just a sketch, but it shows a turbulent flow. I mean, it would be a measurement in one direction, right? I mean, it shows a velocity measurement here as function of x. And what we do so if you want to resolve this, you need a super small mesh to resolve all these fluctuations. That would be DNS, but here we filter, we apply a filter over this, and then you get the black signal. And the black signal, for that you need a much coarser mesh. And typically you make a filter that has a size that's large enough so that the resulting resolution you need corresponds to the money you have in your pocket, okay? So that you can afford to do the simulation. There are different filters that are being used that has some consequence, but maybe we don't need to discuss this here. But you apply the filter then to the equations, and you get equations that look very much like the Reynolds equation I showed you earlier, only that now this residual stress tensor does not incorporate all of the fluctuations, just the fluctuations that you filtered out. So that's what we call here the residual fluctuations. It would just be these fluctuations around the black line, and you see the black line. Actually, it still has a lot of the turbulent fluctuations resolved. One thing I didn't say here, one thing is interesting is that, so all this is resolved, let's say, and all this would be modeled. And it has two big advantages. First of all, we said earlier that all the energy of a turbulent flow is in the large scales. This is a logarithmic plot, and so the small scales, they have very, very little energy. They don't contribute much to you know, mixing on the bigger scale. So if these are resolved, it should be more accurate for predicting, mixing. And then the second big advantage here is we model now only the small scales, but the small scales we said are isotropic, okay? The anisotropy, that's difficult to model. Isotropic turbulence is much easier to model. So that's good. So in general, LES has a lot of advantages. For us, a little bit the issue is that when we think of combustion takes place when fuel and oxygen mix on a molecular scale. So we need to actually know what the very smallest scales do, which need to be modeled here, just like for Reynolds averaging. Okay, so for a long time, people have said LES doesn't really help very much when you are considering reactive flows. But it turns out that these parameters that we use to describe mixing, for example, the dissipation rate, they are determined on the large scale, and they are much more accurately predicted in LES than in RENS. So it is actually much more accurate. So that's the equation, and then here we have this residual stress tensor. As I said earlier, we use here a gradient transport model for this also, and then here we have this eddy viscosity or subfilter eddy viscosity, and for that we use here just this Smagorinsky model. As we saw earlier, here I say this is just a U prime subfilter velocity fluctuation times the subfilter velocity scale, and then for this here I just assume it's LS times is a length scale times the strain, and then this is exactly the Prandtl's mixing length model, but here we call it the Smagorinsky model, and the LS here then is proportional to the filter size. So there's a coefficient here which we call the Smagorinsky constant, and that is roughly 0.2. Okay, so that's what people usually use. But then delta, that's the filter size, and in LES usually we use the grid size as the filter size, and so that's a given. It's always known. So that system is closed. But then LES has one big advantage I didn't mention earlier, that because you solve some of the turbulence, you resolve some of the turbulence, you know part of the dynamics, okay? And so I can use that knowledge of the dynamics of the resolved scale to give me better estimations on what happens on the small scale. So that's done with a so-called dynamic model. The dynamic model says, it goes like this. So basically what the dynamic model does is you have a certain part of the turbulence is resolved. You know that part of the turbulence. And then you say, I have a model which has a coefficient here, this Smagorinsky constant. It's 0.2, but of course not always 0.2, it can be larger or smaller. But you know a part of the turbulence, so you apply that, you write that model for the part of the turbulence that you know, and then you can, from this, you can determine what coefficient would you need that the model for that part of the turbulence is correct, okay? So that determines then the coefficient, and you say, I determined this on the large scales, but it should be valid also on the small scales. That's what the dynamic model does. So you have the residual model here, and then you filter that residual model to a larger scale. So there's a test filter size, which is twice as large, but you can also write the Smagorinsky model for that larger scale, and then you can take the difference of these, and then, so here you always have this term is unknown, but if I take the difference of these, then this term goes away, and all of these, you see all of these are terms that are just evaluated with the mean velocity, so I can evaluate here the right-hand side. The left-hand side is the model, so here I use the Smagorinsky model for the small scale, and then the Smagorinsky model and I filter this to the larger scale, and I use this Smagorinsky model that's written for the larger scale. So I can evaluate, I can plug all this in, and you see this is Smagorinsky constant. I can solve this whole equation for Smagorinsky constant. And you know, now I have a value that I can use. So this is so it gives me this equation, and I can solve it here for the Smagorinsky constant. But the point here again is this leaves you with a model that has no adjustable coefficients anymore. That's beautiful. That's very nice. Okay, so right. So that was a little short course on large eddy simulation. So one more thing, you know, for large eddy simulation, because you filter out only a very small part of the turbulence, usually the viscous terms that we always neglected when we talked about RANs, they cannot be neglected in LES. So keep that in mind when you ever want to do LES. Okay, so, and then we go back to combustion. We want to talk about the physics of turbulent premixed combustion first. And then we talk a little bit about non-premixed combustion, and then we'll talk about modeling. And so this, I showed this earlier. This is a stationary gas turbine. You have here the turbulent flow field. These are the velocities. And then here the surface is actually the flame surface. And you see this is LES. So you see part of the turbulent fluctuations, they are resolved, but you know that flame tries to burn into the unburned mixture. So if we want to understand now, so what we want to understand now is, yesterday we talked about laminar flames. We talked about, you know, what's the structure of a laminar flame, a reaction zone and preheat zone. We defined length scale of the reaction zone, preheat zone, and so on. And now we talked about turbulence, and we had length scales of turbulence and all that. And so the question now is, how do these two interact? Do they interact? Is there an effect of the turbulence on the on combustion, on the flame? And one could also answer the question, is there an effect of the flame on the turbulence? But that's a much more complicated question, and we're not going to touch that. But in order to do this, to compare the scales now of the turbulence and the flame, we're introducing, you know, some of these scales here again, or summarizing the scales that we have already defined. So you have the large scales of the turbulence, and the large scales of the turbulence obviously are the large eddies, obviously are those that create flame surface. You know, when you have a laminar flame and you add turbulence, then you make flame surface. Larger flame surface burns faster, so that must be important. So we said in terms of K and epsilon, we can define a length scale here, K to the 3½ divided by epsilon. We can define a U prime, and we can define a time scale. Okay? These are the large scales. And then we said the very smaller scales, they might be of interest because we said typically flames are very thin. And so maybe the large scales of the turbulence, they are much larger than a flame. But the small scales of turbulence, I mean, depending on the Reynolds number, they get smaller, smaller, smaller. So, you know, by changing Reynolds number, I can make these as small as I want. And so maybe these interact then with the inner structure of a flame. And so these are important also. So we had the Kolmogorov scale, Kolmogorov velocity, and the Kolmogorov time, you know, which is then here the smallest eddies here expressed in terms of nu and epsilon. And then we had the scales of the flame, where we said we have a flame thickness, we have a flame speed, and you know, diffusivity. And so these are how these are connected. For Lewis number equal 1, we can say D is lambda over rho Cp, and so that's the same thing then. And we have a flame time, and so on. So, and then we said the flame thickness actually is the preheat region and the reaction zone. And remember yesterday we said in the preheat region, it's chemically inert, there are no reactions. All the reactions happen in the reaction zone. And so the reaction zone is much thinner than the preheat region. So here we don't want to define also a reaction zone thickness. So LF is the flame thickness, L delta is the reaction zone thickness. So this gray area here, that would be LF, and then L delta is a small part of this. And we want to say, we want to define it in a way where we say L delta is just a tenth of the flame thickness. You know, it's 0.1 times flame thickness. Okay, and then we can, you know, look at here the non-dimensional numbers. Schmidt numbers nu over d, we want to say that's equal to 1. And then we can write the Reynolds number. The Reynolds number, the turbulence Reynolds number is LT times U prime divided by nu, or divided by d, okay? But d is equal to LF times SL, according to this. So I can write the Reynolds number as LT divided by LF times U prime divided by SL. Okay, so that's an interesting way to look at it. We have expressed the Reynolds number as the ratio of the velocity and the length scale of turbulence and the flame. Okay, so we want to do this also for the other quantities. Here we have a Dampf-Köhler number. Dampf-Köhler number is the chemical time scale or the flame time scale. Is a turbulent time scale divided by the flame time scale. Turbulent time scale is LT divided by U prime. Flame time scale is LF divided by SL. And then also here, I have these ratios of length scale and time scale of flame and turbulence. And then another interesting quantity we want to define is what we call the Karlowitz number. And the Karlowitz number is, it measures it expresses the ratio of the flame time to the Kolmogorov time scale. So I said earlier, maybe the Kolmogorov eddies, they interact with the flame, and so that's what the Karlowitz number expresses. Okay, so I can, if I write it like this, I can also, you know, just with these relations here, I can also write the Karlowitz number like this. So it's LF squared divided by eta squared. That's a length scale ratio. And then using here the definition of eta, here the definition of eta, and also here this relation for epsilon, then I get something that has again LT and U prime, and so I get this. So Karlowitz number, it can also be now written as a combination of these ratios of length scale and velocity scales. Okay, so then from this we can construct here what we call the premixed, turbulent premixed regime diagram, and this is often called, or let's say a sub version or an early version of this is called the Boge diagram, which has here these lines, which doesn't have this line, and this here I would call this the Boge-Peters diagram. Peters added, you know, this distinction here also, and basically, I mean, it shows U prime over SL, so the ratio of the velocities as function of LT over LF, the ratio of the length scales. And because I've expressed these numbers exactly as these ratios, I can, and you know, on a log-log scale, and then I can put in the numbers here. You know, for example, I can put lines of constant Reynolds number, Karlowitz number, and Dampf-Köhler number in this diagram. So here, for example, for the Reynolds number, you can say U prime over SL is the Reynolds number times LT over LF to the -1, okay? So in a log-log plot, that gives you a line with a slope of -1 then. And so this is this line. And if I set the Reynolds number equal to 1, it has to go through the point 1, 1. And so that's here. So that is this line. And so in this region, the Reynolds number is smaller than 1. In this region, it's larger than 1. So smaller than 1 means it's laminar. So we call this laminar flames. And all this is turbulent flames. Okay? So that's number 1. And then the Damköhler number here, you see, is U prime over Z. Bring this to the other side. Is then proportional to LT over LF. So that gives you just a line here, or it's not shown actually. That gives you a line with a slope of 1. And then we have the Karlowitz number. So the Karlowitz number so for the Karlowitz number, we have U prime over SL is equal to the Karlowitz number squared, right? Karlowitz number squared times LT over LF times LT over LF, LT over LF to the 1/3. 1/3, and then here also 1/3. But this here is just a constant. Now we set the Karlowitz number equal to 1. That means, again, it needs to go through this 1, 1 point. And then it is a line that has a slope of 1/3. So that's the slope of 1/3 here. And so that's that line. And then we also want to have a line where we say Karlowitz delta is equal to 1, meaning Karlowitz number is LF divided by eta squared, and Karlowitz delta is then the reaction zone thickness divided by eta squared. And so that is then nothing else than delta squared times Karlowitz number, where delta is this ratio of L delta and LF. So this is 100 times larger. So that's why it has the same slope. You know, it just goes to this point 100. Okay, and now we can try to understand what this means. Especially the Karlowitz number is very interesting because it compares. I mean, if you think of it in terms of length scales, it compares the flame thickness with the Kolmogorov scale. So what does that mean? It means if the Karlowitz number is very, very large, very, very small, then even the Kolmogorov scale is very, very large compared with the flame thickness. Okay? And that means, so when we say larger or smaller, it's easiest always to think much, much larger and much, much smaller. Okay? So if even the smallest scale of the turbulence is much, much larger than the flame thickness, then I can treat the flame as infinitely thin compared with the turbulence, right? So it's an infinitely thin flame. So if we're in the regime where the Karlowitz number is smaller than 1, then we're in a regime where the flame is infinitely thin compared with the turbulence. And so there's another line here which is not very important. So look at just all of this as the same regime. We call this then the corrugated flamelet regime. Corrugated between, you can look at the flame as a surface, an infinitely thin flame surface, and all the turbulence does, it can wrinkle or corrugate the surface and create larger flame surface. This is also called here the Klimov-Williams criterion for distinguishing these thin flamelets as opposed to a regime where the turbulence then interacts with the flame structure. So these are examples here from simulation and from experiment. You see here a simulation of a turbulent premixed flame that burns here from left to right in a turbulent flow, and where the flame is basically infinitely thin compared with the turbulent scales. And this here is a LIF, laser-induced fluorescence of the OH radicals. So this shows you in a turbulent flame, it shows you just one plane, one slice cut out. And then you see this here is the, so this OH. So you see here you get no OH whatsoever. here you have OH in the equilibrium region, and you see the transition for OH from nothing to very much. It really, seems to appear on an infinitely thin front. And so that is a flame, that's a turbulent flame in the corrugated flamelet regime. And then, so this corrugated flamelet, and then we can look at the broken reaction zones regime. On the other side, before then we look at this thin reaction zones regime. So in the corrugated flamelet regime, we said the smallest eddy of the turbulence is much, much larger than the flame thickness, entire flame thickness, right? But now I can look at the opposite end of the spectrum, where, say, the turbulent eddies, they're very, very tiny, the Kolmogorov eddies, they're very, very tiny. They're not even not only just smaller than the flame thickness, they're smaller than the reaction zone thickness. And then the Kolmogorov eddies, they mix inside the reaction zone, and so they destroy the laminar flame structure, and by this, there is no coherent reaction zone anymore, but is a distributed reaction zone or a broken reaction zone. So that's then called the broken reaction zone regime, or also the distributed reactions regime. So that's where mixing is much, much faster than the flames timescales, for example. And this here shows an example here by Andy Aspden. He did simulations of basically this is a supernova type of flame where he computed, where the transport mechanisms are very different, but still there's a small Karlovitz number, and then you see again small Karlovitz number. You see really the like a laminar flame structure, and then for a very large Karlovitz number, you see here there's no coherent reaction zone. Reactions are kind of all over the place. So in this regime then, you can have local extinction, and it can lead to global flame extinction, similar to what we discussed yesterday, the premixed, the non-premixed flames. As soon as the mixing gets faster than the chemical reactions, or the chemical reactions are slower than mixing, the reactions can't keep up, and then flames extinguish. And that's the same here. If you are in that regime, then it's likely that a flame would just blow out. If you don't do anything special to stabilize the heat release process. Okay, and then we're left with this regime in between, where we would say now we're looking at a regime where the Kolmogorov scale is much, much smaller than the flame thickness. So the Kolmogorov scale, the Kolmogorov eddy, actually it comes into the preheat region, but the reaction zone is still much, much smaller than the Kolmogorov scale. Okay, so an example here maybe could look like this. We have a flame that looks like this, and is propagating, here's unburned and here's burnt. So it's propagating from right to left. And then I have a preheat region which kind of looks like this. And so I want to say, so this here is LF. Okay, and then I want to say this line here, that should actually be the reaction zone, okay? Very, very thin reaction zone. And then I have Kolmogorov eddies, which are kind of this size. So they kind of go into the preheat region. They mix in the preheat region, but they can just corrugate the reaction zone, but they cannot enter the reaction zone, okay? So that's what we call then thin reaction zones regime, where this happens. And this shows an example for this, where we have, again from a DNS, flame propagates here from right to left. So you see here's equilibrium region, here's unburned, and then you see the so it's not infinitely thin front, because you see here regions, you know, where parts of the, you know, hotter part appears here on, you know, the cold region and vice versa. But it seems like here the change from unburnt to burnt still happens in a very thin region. And, you know, similarly, people have done, maybe it would be more instructive, or you might see this on the next slides, to show a radical then, which really is not present here in the preheat region. It's only present in the reaction zone. But the preheat region, you see here very clearly, turbulent mixing plays a part in this regime. And then this here shows, again, this is a different example, here again from Andy Aspden. He computed here 4 different flames in the thin reaction zones regime and also into the broken reaction zones regime. And you see here low Karlovitz number, higher, higher, higher. Don't worry about the exact numbers here of the Karlovitz numbers. I think the definition is a little different from what we have used here. But you see this low Dampkeller number, Karlovitz number here, gives you again a, you know, something in the thin reactions or in the corrugated flame regime. You don't see any turbulent mixing inside the flame. And when I go to the higher and higher Karlovitz numbers, you see much more of that. And again, here you see how turbulent mixing, you know, maybe helps in advancing the flame here even more. And then you get to a regime here where reactions are seemingly kind of all over the place. Now, if I look at the burning rate, well, you see here, you know, it becomes a little wider, even though even at this very high Karlovitz number, it doesn't seem to be all over the place. These are hydrogen flames. You know, we said earlier, hydrogen has these thermodiffusive instabilities. And you kind of see this also. This is the reason why here it seems like you get quenching, very low reaction rate, and here you get high reaction rate that comes from this instability. This here, just a word of caution. When we derived this Borghi-Peters diagram, we made a lot of assumptions. We said the kinematic viscosity is equal to diffusivity. You know, we said, you know, we made a lot of assumptions like this. We said Schmidt numbers are equal to 1, and what else? Nu equal to D. We said this ratio here, LS, we said nu is equal to SL times LF, and so on. So we made this assumption here. But when you evaluate this in a real flame, here methane air flame, you see these numbers are different. And if I would use real numbers, then these lines might end up in a different place, okay? So don't, I mean, this is how we usually look at this. Don't look at these lines like, you know, they must be exactly there. So for example, here, you know, I would say this one here, is this in the thin reaction zones or in the broken reaction zones regime? We don't know because this line is not exactly there. We just know if we go from a point of smaller Karlovitz number to higher Karlovitz number, we move in that towards that direction. And so again, that's just a word of caution. Don't take the positions in a diagram like this too literally. This shows a simulation here of 4 different methane air premixed flames that was done here by Antonio Attilli together with Fabrizio Bizzetti, and when they were together at KAUST. And so it shows 4 different cases, and it's an interesting data set because they try to put it together so that the Karlovitz number is the same for all of these, and the Reynolds number changes from small to large. And they do this by just changing here the nozzle diameter, or the, I mean, it's actually a planar flame, so it's a nozzle width. They have the jet width here, they have changed. And again, you see, you know, these can be quite expensive. And you also see here jet Reynolds number. That's roughly what I said earlier here, 22,000. That's roughly what we can do. Anyways, yeah, this shows these flames here in this regime diagram. We don't need to focus on this too much. But what's interesting is now we can try to see, you know, what is the regime? I mean, how do you measure the regime? You can look at the flame thickness. You can measure the flame thickness. and then compare it with the laminar flame thickness. You know, if it's the same, then you're in the corrugated flame regime, and if it's not the same, then it might be something else. So what's shown here, this is the PDF of, so the probability density function of the local temperature gradient in the preheat region. The temperature gradient now is basically the inverse of the flame thickness, right? I mean, if you look at a quantity like this, so because it's normalized here with a laminar gradient, then I mean it has dimensions of temperature per meter, Kelvin per meter, and take the inverse of this, then it has unit meter. I mean, if you normalize the Kelvin out. So this is the inverse of a flame thickness. The value of 1 would be the laminar flame thickness. Smaller values meaning you get a larger flame thickness than the laminar value. You see this here, this is logarithmic scale. You see the maximum values are kind of here. So the flame thickness you find is about 10 times larger, roughly, than the laminar flame would be. And that indicates you have turbulent mixing in the preheat region, and it just makes the preheat region much, much larger than a laminar flame without the turbulence would be. Now, if we look at the same quantity in the reaction zone, then you see the maximum is roughly here, which is, you know, roughly almost exactly the laminar value. So these flames are all in a regime where the preheat region is very wide, you know, from the turbulence, but the reaction zone is basically has the thickness of the laminar reaction zone. Okay, so all these flames seem to be in the thin reaction zones regime. And one other thing that's interesting, there are many different cases here, but they all seem to be the same. There's very little difference because they all have the same Karlovitz number. Okay, they all come out to be the same in this, you know, in these ratios, which is what you should expect if the Karlovitz number is a meaningful quantity. And then we can look at the flame structure. So what this is now is for the 4 different flames is the heat release rate, you know, as function of temperature. So so you see each locally evaluated heat release rate and the temperature are plotted with these points, and then the line, which one? I don't know which. The red one is the conditional mean. So that's the mean. So it's a given temperature, and then all data points averaged at that temperature. Okay, and then here, let's say at this temperature, all the data points at this temperature averaged. That's conditional average, right? So, and then the black line, that's just a one-dimensional laminar flame. Okay, and you see the heat release rate is exactly the same as a laminar flame. So that's what we would expect if this in the thin reaction zones regime. And it also shows that in the thin reaction zones regime, really, even though the preheat region was very strongly affected by the turbulence, 10 times larger, the structure in the reaction zone is still the same as in a laminar flame. That's very interesting. It's very important for modeling also. I should say also, which I didn't say, I mean, which of the regimes is technically the most relevant? I mean, I can discuss regimes up and down. If I tell you about a regime that in practical applications doesn't exist, it's not very useful, right? Now, as an engineer, which regime would you pick? You don't pick regimes as an engineer. As an engineer, you try to build a device, and you want to make the device such that it works. And so usually you want to have a device as small as possible, which means the heat release should be as large as possible. So you try to make the turbulence as strong as possible. If you make the turbulence too strong, the flame will blow out. It will extinguish, which means you stop making the turbulence faster at some point. Yeah, what is this point? It's just before it extinguishes, and that's exactly you know, in this regime diagram, that would be exactly just below this line, right? Because here, you know, things start to extinguish. Here they're still burning, but they're very, I mean, very, very strong turbulence. So usually we engineer devices to be in the thin reaction zones regime. That's the bottom line of this. Okay, and then we can think, so now, you know, we know a little bit about the physics, and now we can think of the burning velocity. So for laminar flames, we introduce the burning velocity. For turbulent flames, we can also introduce a turbulent burning velocity, which is the velocity that, with which a turbulent flame propagates under the influence of the turbulence. And so we have identified two important regimes. You know, one can imagine that that the way we model these should be different in the different regimes because the physical interaction also is different. But the first question we should ask is the impact of turbulence on the flame, is it really important? Okay? Does it lead to a higher burning velocity than the laminar burning velocity? And we can look at this here in this plot I showed earlier. So if we think of internal combustion engines, they are at high pressure and high temperature. And we said yesterday, if I start out at 1 bar and 300 Kelvin, and I do an isentropic compression here with a pressure ratio of 20, then I get a burning velocity which is maybe 80 centimeter per second, okay? So let's keep that in mind, 80 centimeter per second. This is actually an experiment that was done in an engine. So what they do is they run the engine, they measure the pressure, and then from the pressure they infer how fast the flame must have burned. Okay, so it's not a, you know, I mean, it's not a laser experiment, but it shows you how fast the flame must burn. And they do this here as function of the Drehzahl, which is RPM, right? So the speed of the engine. And what they find is, you know, you get roughly 15 meter per second. 15 meter per second, here we were less than 1 meter per second. Okay, so it's a factor of more than 15, but let's say a factor of 20. That factor of 20 must come from the turbulence, okay? Because the otherwise thermodynamic conditions here are the same. So, yes, the turbulence has a very strong influence. Here's another one where we see, you know, from these are just burner experiments, where you see the turbulent burning velocity as function of the velocity fluctuation. And you see values here also of roughly maybe 10 or, you know, 10 to 15. And for this case, the laminar burning velocity is 0.4, which means you get a factor of roughly 30. And that factor of roughly 30, that must come from the turbulence. So the turbulence creates a huge effect on the flame speed. Now we said we have two different regimes in which the interaction between turbulence and the flame is different. And so that was realized here by Dammköhler and here in the 1940s. And Dammköhler then, he came up with models for the turbulent burning velocity that would describe the physics in these individual regimes. So he called it, now we call this corrugated flame regime and the thin reaction zones regime, he called it the large-scale turbulence and the small-scale turbulence regime. So we want to look at these individually. Now for a flame, okay, let's say you have a turbulent flame like this. This is unburned, this is burnt. So this burns from left to right. And then I can, you know, I can think about, you know, how much fuel is burnt per unit time. That gives you the heat release rate. And you could say, well, the heat release rate is the density times the surface times the speed of the surface, right? That's what it is. So the instantaneous flame front, it has a surface AT, a very large surface, let's say, and it burns locally with the laminar flame speed. Why with the laminar flame speed? Because we said in that regime, the corrugated flame rate regime, which we're considering now, the flame is so thin that the structure of the flame is not disturbed by the turbulence. Okay, so it burns locally with the laminar flame speed. And then I can say, okay, this is the real turbulent flame. So I take a photo of this. This is one instantaneous realization. But let's say I take 1,000 photos of this, then I get a mean flame front position, which kind of looks like this. So that would be the mean flame front position, and the mean flame then, the average flame, it has a much smaller surface area, right? Because this is much smaller surface area than this corrugated one. But we say now, to compensate for this, this burns with a faster velocity, such that it gives us the same mass burning rate as this one. So this has high area and small velocity, and this is a lower area, so it needs higher velocity. That, what I just said, is expressed here in this equation. The mass burning rate is the unburned density, here actually in both cases, and then for the local instantaneous flame, the laminar flame speed times the area, here this area, and then for the average flame, it is, again, the density times the area of the average flame times a turbulent burning velocity. These must be the same. The density goes out, and then St divided by SL is equal to AT divided by A. Okay, so the ratio of the burning velocity to the laminar burning velocity is the turbulent flame area divided by the mean flame area. Okay, so that gives us an expression already. But the question is, how large is the turbulent flame area, compared to some average like this? How large is the wrinkling? And for this, Damköhler used a little trick. He was thinking, well, in my lab, I had this Bunsen burner, and it was the same thing. When I increase the flow rate, then I burn more with the same laminar flame speed. I burn more fuel, right? I mean, if I crank up the flow rate in the Bunsen burner, then I get higher heat release, total heat release, because I burn more fuel in the same time. How does the flame do this? It locally doesn't burn faster. It makes the area larger, right? I mean, you get a more pointy flame, and so that has a larger flame area. So he thought, I just use the same concept now for the turbulent flame. So here you see the turbulent flame. Here you see the turbulent flame. And let's look at this little piece here as like a little Bunsen burner, where in the Bunsen burner you have an incoming velocity here, you unburned. And here we want to say, that should be the eddy here. You have an eddy like this, or an eddy like this, which then has a U prime that causes this disturbance here on the flame. And then here for the laminar flame, we had SL was U unburned times the sine of this angle, and for the here we want to say the sine of the angle now is SL divided by this U prime. Okay, that's the same as this. And now we want to relate, so we are interested in this area. How much larger does the area have to be? And this area divided by here the base area can be expressed also here by the sine of this angle. So it's basically this here divided by this, and that's also the sine of this angle. And so this means I can replace here, or here, I can replace AT divided by A by this angle, and the angle I can replace here by SL over U prime. And so ST divided by SL then is nothing else than U prime over SL, okay? So that's what you get with this, from this analogy with the Bunsen burner. And then there's a 1 added here. Why is the 1 added? So that it takes the limit of a laminar flame also. If in the limit of a laminar flame, U prime is 0, and then ST should be the same as SL, right? It still burns with SL even if there's no turbulence. That's why you have this 1 added to this. Okay, so that is the model for the turbulent burning velocity in the corrugated flame regime. And that's interesting because it shows why internal combustion engines work. If you think of a spark ignition engine, you can run the spark ignition engine at 500 RPM. You can also run it at 10,000 RPM, okay? Somehow it still works. And why is that? I mean, you know, if you run it at 500 RPM, you have a lot of time for combustion, right? Very slow, a lot of time for combustion. At 5,000 RPM, you have a lot less, time for combustion. Why do you still have enough time for combustion if you make the speed higher and higher? Well, because if I make the speed higher and higher, the RPM higher and higher, the piston speed gets larger, the U prime that you have in an engine, it comes from the piston speed, okay? So the U prime is proportional to the piston speed, which means that also the burning velocity is proportional to the piston speed. Isn't that beautiful again? I mean, did Otto think of this? Probably yes. He was a good buddy with Dampköhler, and they, had a beer together. It wasn't the same time, though, unfortunately. But anyways, I mean, it's interesting that this explains why you can run an engine even at, 20,000 RPM, where you have no time, because you get stronger turbulence, which means the flame just burns faster. Okay, good. So maybe we'll stop here and take the next break.